So yes, my name is Daniel Pezely. I'm with Splunk. The title of this talk is, it's about LDB, the Lethe database. Some of you who may have been at prior Erlang factory conferences in San Francisco the past 2 years would have heard from some of the BugSense founders. BugSense has been acquired by Splunk. I inherited the code, and I'll get into some of these details. So what I'm going to talk about is we had a LinkedIn module written in C that implemented a Lisp dialect of Scheme. And we found that by rewriting what we were using, what our intention for that feature was, by rewriting it as a pure Erlang module, we had a 10x performance increase after about 4 months. We've actually gone up from there, but I'll get into that. So this is a classic Far Side comic strip. For those of you who may not be able to see, there are 2 aliens. One has a couple of humans in a jar, and the other is saying, remember, this time, punch holes in the lid. And that's kind of the theme of this talk. It's about the details. Remember to punch holes in the lid. So just how I'm going to present this. So I'll move somewhat quickly, because I know we're kind of compressed for time. But also, one of the benefits of being one of the last speakers or in the last time slot of a conference, I get the benefit of everyone who's presented before me. So the session that was in this room before on debugging complex systems, all of that applies. So hopefully you got that. If you didn't, if you weren't here for that session, you can get it in the archives once that comes out. So if this were a 3-act play, the middle act would be the bottleneck, the performance, and all those details. And there will be an epilogue for those who want to take it to 100x beyond the initial 10x. I'll touch on some of those, but that'll be at a high level. So first, some background. So I mentioned the name BugSense. For those of you who aren't familiar with the name, BugSense is a company that was founded in Greece about 2 years ago. And chances are good that you have their SDK on your mobile phone, on your tablet, and so on. The essence of the company is to harvest crash reports. In addition to that, some features that have been added over the past year have been more visitor analytics, traditional metrics that you might be familiar with from, say, Omniture, which is now Adobe. So the way we harvest that part, the metrics, goes into the Lethe database, LDB. So I may use the names interchangeably. The important thing about our system is it's a stream processor. Now, not everyone knows what a stream processor. Probably half of the people at an Erlang conference do understand what it is. But for those who don't, I'd like to make the comparison between data flow versus workflow. No, not data flow. There's a hardware architecture and software architecture that uses that name also. But one in contrast to the other. Data flow versus workflow. With data flow or with a stream processor, the idea is to move through the pipeline as efficiently as possible, and every decision that you make is how can you move the data one step further down the pipeline. Secondary to that is any transformation that you would make on the data. So that's what we mean by a stream processor. So we take data from millions of devices, actually hundreds of millions of devices, and BugSense has been considered an Erlang success story for the past few years. And some of the earlier articles, as noted down here, I won't get too much into historically what BugSense has done or what the Lethe database was years ago. There are good quality articles. High Scalability has an article. If you just search Erlang or Erlang Lisp and C, if there are too many Erlang articles, you're sure to find John's guest post on there. A little bit about my background. There's a little blurb, my bio, which was included when you found this talk. But one thing of my early experience, when I was an undergraduate in 1990, I was working in virtual reality at that time. And one of the things that influenced me was when you're trying to build a really complex system like that, when you're trying to model reality, well, everything else seems to be a subset. When you're building for all that complexity, when you're designing for that, and it didn't work. I mean, obviously, I'm not known for virtual reality, so we had a ways to go. We had to invent things that didn't exist yet, but that's a story for another time. But through that, we live our lives. We view through the lens of our experience, and I'm sure you've heard various quotes similar to that. So this was no different. When I inherited this project, part of it to me was there were some obvious issues, some obvious places where there was room for improvement. And then there were other areas that, for many people, would have seemed to be the first place to start. So anyway, I'll get into some of those different elements. But I want to point out this last line on here. I'm new to Erlang, so that's also another component to this talk. Someone who's new to Erlang, but an experienced developer, an experienced software engineer, coming in, picking up Erlang, so is already familiar with functional programming from Common Lisp. I've been doing high-performance Common Lisp for 6 years prior to Splunk. So part of this is also to include the learning curve that I went through. So as the title gave it away, we had a 10x performance increase. But what were the numbers? So we were at 200 requests per second. Now we're at 2,000. Actually, the 2,000 was at about the 4 or 5 month mark. And since then, we've gone up since then. I think we're probably at about 20, 25 increase. So the hardware that we're running on, we're on the Haswell servers at Amazon. We get several billion requests. So single-digit billions, but still many billions per day. The servers that we use have 30 gigs of RAM, and that one server may have upwards of 30,000 customers. Now, of course, they're not all active at one time. We also have machines, a server instance that will be dedicated for one customer, but that may give you some idea of what these numbers mean when we say 200 per second, 200 requests per second versus 2,000 requests per second. So the use cases. So as I mentioned, basic analytics and advanced analytics similar to visitor journey data that you may be familiar with if you use, say, Google Analytics. And I mentioned some of the others earlier. We have other components that deal with the other elements of data that we harvest. So I mentioned crash reporting. So if you're familiar with developing for iOS or Android, one of the techniques that developers will use there is to strip the symbols out of their executable. This way, competitors can't see what they're doing. But it makes it difficult to see your own crash report. So that step to remate that symbol information is called symbolication. So we have other systems that do that. And hopefully, at an upcoming Erlang Factory, the other guys will present those systems as well. So our operational criteria is very similar to what someone would have in an early stage startup. When BugSense was acquired by Splunk, it was basically nothing changed in that. I mean, they moved from their early service provider to AWS, added a few more server instances, but not a whole lot changed. So we still operate with the same model. But it's also important to point out, our traffic is steady around the world. We have a lot of big customers in Japan and Europe, the United States. And due to that, if we had a queue for all this data, we would never be able to get caught up. So it's just one of the realities that we have. Other people have peaks, they have lulls, so that's not a criteria for them, but it is important to us to eliminate queues. So I already mentioned that we focus on data motion, which again is another way, if you read the academic literature, what I talk about data flow, some people will refer to it as data motion. And again, it's going back to we have a stream processor. So it's also important that when we receive data from a mobile device that we respond within milliseconds, single-digit milliseconds. And telecommunications also have this hard requirement. Ad networks will also have this requirement. The nature of the data that we have, it's a lot of counters, probabilistic counters and linear counters. So for probabilistic counters, again, on highscalability.com, there's an excellent article on how to count 1 billion unique items. So I highly recommend that for anyone who's interested in that topic. And I'll touch more on that in a bit. So the languages that we have, so Erlang, Lisp, and C, as I mentioned. Erlang, OK, we're at an Erlang conference, so obviously you understand why we're using Erlang and why it was chosen early on. Our top-level code was in Erlang. And again, now with the pure rewrite, it's all in Erlang. But it's also important to point that we have a long-lived port. So some of you may be exploring, do you want to have a LinkedIn module, and you're just learning about ports. So I'm not going to get into those details. The Erlang documentation and other tutorials are sufficient to guide you through that path. I just wanted to give you some additional context. So that's the essence of why I'm presenting today, not to be a tutorial on how to build a port. So, but also, I didn't build a port. I inherited the code, and part of it was to find the problem and resolve it. So these ports are long-lived. Now, many people will have a port command. They'll have a LinkedIn module, and they're just computing some value. The function returns in milliseconds, and you probably won't have any of the issues that we ran into. For us, we were also using this long-lived port for our data storage. So, so the next two pieces, the Lisp and C. So the Lisp dialect was Scheme. It was an R4 dialect for those that are interested. The reason it was chosen, Lisp is a very malleable language. Now, as a short aside, Joe Armstrong gives an excellent presentation on how malleable Erlang is. And it is malleable, but the example that he used when I saw him give this presentation was about implementing crypto types of things. So he had an implementation of the RSA algorithm, and the top level code reads like a spec, which is a wonderful thing. But sometimes you're not even at that level. So an early stage startup needs something that's malleable because you don't know what your problem space is, let alone what your solution space will look like. So it was the right decision at the time. And we'll revisit that notion in a moment. But on to the C part. So it's also important that the implementation of Lisp that we had, it was essentially an interpreter, but calling it an interpreter is almost too generous. It's parsed, like in the sense of Tickle, if any of you are familiar with that. So it's a very, I don't want to say a weak implementation, but it is what it is, but it wasn't a robust Lisp system like you would find with SBCL and Common Lisp. So we also implemented all of our counters, like I mentioned, and all of our storage. So our hash tables were implemented in C, and that gets to the root of the problem. So the nature of the data that we're storing, so key value pairs, sets, which are essentially arrays, and the probabilistic counter, so hyperlog-log, or HLL, as it's sometimes referred to. So with the earlier architecture, everything ran in one process space. We had one Erlang process per customer. And we could handle this based upon the messages that were coming in. There was a customer ID associated. The process would exit when idle, which many people, is a common pattern that you'll see in Erlang code. Also, regarding one of the principles of Erlang, let it crash. Well, we would also allow that, but at the operating system level. We would let it crash hard. So I mentioned that there were some flaws with, or not some flaws, but some limitations to the C-based implementation of Lisp. We had no garbage collection. So memory would grow and grow and grow and grow. So eventually the Linux out-of-memory killer would do away with it. But fortunately, it would come back. Beam, the virtual machine, would come back within milliseconds. So for our operational characteristics, our operational needs, that was sufficient. Well, I should say not ours, because these were the decisions made before I was involved. So it worked for an early stage startup. It worked to help them get acquired. And the operation, it's still in operation today. That early system is still in production right now. So one other thing that's critical to point out is this last line. High traffic customers were throttled. So I say may be throttled, but actually they were throttled. All of them were throttled. So we're in a statistical modeling world. So the proper way of phrasing it there is to say that we were doing subsampling. Now, sometimes you want to be able to do this for a brownout type of notion. And for those who may not be familiar with that term, blackout versus brownout. Most people associate this with the electric company. An electrical storm comes in, you have a blackout, everyone's without power. But in the summertime, the air conditioning is running, too many people are drawing too much power. The power company, the electric company, may intentionally force what looks like a blackout to all of us, but it's intentional, so they call that a brownout. So sometimes you may want that capability, but the point here is we had to use this capability because, again, we could only handle 200 requests per second on one server instance. So as I mentioned, room for improvement. So when you talk about an Erlang server to someone who has just a vague notion of Erlang, their mental image is likely to be a system that can handle thousands or tens of thousands of requests per second. 200 is kind of pitiful, to be honest. So we knew there was room for improvement there. But we also had a revelation, and this is one of the points that I said we'd revisit. The early stage startup had certain needs, but 2 years on and after acquisition, those needs were not the same. So we no longer needed something as malleable as Lisp. So we revisited that. And that's an important thing for an organization as it matures to realize, OK, we need to revisit the original criteria and maybe throw some of them out, some of the items out. So we love Lisp. And like I said, prior to Splunk, Common Lisp was my bread and butter. It was my server language, and I write a little bit of JavaScript for the front-end work. But I mean, I wrote code for the decision maker at an ad network in Common Lisp, a high-performance recommender system, and so on. So, you know, the geek in me, I'm sure we have a lot of language geeks in here. So, you know, as a language geek, you know, I didn't want to let it go. But it was the right business decision to do. So, so we had the premise that even though there were known limitations, my own experience pointed to there was probably a problem on misuse of compare and swap primitives. So the emphasis there should be on the misuse. So, and I'll speak more about compare and swap in a moment. So we needed to make sure that it was what we thought it was. Now, as I mentioned, the preceding talk on how to debug complex systems, all of that applies. So I highly recommend, you know, using all the tools that the previous fellow recommended. But in our case, like I said, call it intuition, call it experience, call it dumb luck. But anyway, we started with the experiment. So we didn't use dtrace, strace, or anything like that. So in this case, the experiment was, let's eliminate the Lisp portion. Let's eliminate the C code that implements Lisps. That's where there was a lot of complexity. Only have cheap counters. I should also mention, we have the ability in our server farm with another Erlang application to mirror production traffic. So this is a production environment with production traffic, but we don't need to rely on the results of that traffic passing through our server. So I mean, we're very fortunate in that regard that we have that capability. So by forking our own code, we had the LinkedIn module that would return within a few milliseconds. Now, it's also important for those who are just exploring, just entering the whole LinkedIn module business, this notion of reductions. So the Erlang scheduler, well, let me back up a second. It's best to think of the way an Erlang process works. You have the functions that are executing, but it takes some amount of time. So that unit of time for which to measure the execution time is a reduction, or reduction counting. Now, I'm glossing over the details, but I just want to highlight for those that are new to Erlang LinkedIn modules and ports, learn about reductions, make sure you understand it, because that becomes very important. So again, back to our experiment, we made sure that the experimental branch would return within a few reductions. So what we observed was only a marginal increase in performance. So that led to a confirmation that, OK, if we saw a huge increase, well, the huge increase then would have implied that it was the C implementation of Lisp. But it was a marginal increase. So that code probably was not to blame. So this reinforces the notion that it's probably something else that was still in the code path. So we went with my notion of it's probably the so-called atomic operations, and I'll explain why I'm saying so-called and putting atomic in quotes. So, so our course of action was to rewrite in pure Erlang. So incidentally, this conference last year, John Vlahogiannis, so he's from Greece, his nickname is John Romero. So if you want to find him on Twitter, you'll have to find it by that name. He gave a talk here last year presenting the old architecture, and after giving his talk, he went to a coffee shop down the street and started writing the pure Erlang version. So just a little side story. So another little detour. How compare and swap can be harmful. And I'm not going to get into all the details. As you can see, there are little footnotes here. So I encourage people to download the slide deck after the conference. But what I want to point out are the things that typically will trip people up. And the middle section of the slide, beware. Lock-free is not necessarily wait-free. So there are multiple definitions of atomic. Compare and swap is atomic in the sense of a transaction, as with a database, all or nothing. It is atomic in that it's indivisible. There's one line of assembly. However, it's not atomic in that it does not occur instantaneously. So depending on the hardware that you have, that one line of assembly could take anywhere from 100 CPU cycles to several hundred CPU cycles. Now, I'm not an expert on the different architectures and where the performance penalties are where, but follow the references, and they get into all the gory details. So this goes back to the comic at the beginning. Remember to punch holes in the lid. If you're going down this path, down this rabbit hole of a long-lived LinkedIn module, a long-lived port, you need to be aware of these things. So again, we were using the C code for our data storage layer. So it was long-lived. We also needed to have either some kind of locking mechanism or some kind of compare and swap type of mechanism. So these were the issues. So these are the issues that I wanted to call out. So I also want to emphasize the first sentence that's on here. Compare and swap as a simple replacement for locks is worse than naive, because a naive approach is uninfluenced by locking methodology. So you almost would be better getting a student who knows nothing about locks and say, OK, read this material about compare and swap and go write an algorithm for us. You'll probably do better than taking someone who's been in the business for a while and my brain is all muddled by all these different approaches. And I have made all these mistakes. So I'm not criticizing the people who wrote the code before me. I've been there, done that. So back to our specific problem. So as I mentioned, we had a few different places to look for where our performance bottleneck was. So the theme here is strive for 10x or more performance gains. There were lots of things that we could have done. We could have implemented a proper compiler. We could have implemented garbage collection and all these other elements for the Lisp system. And again, I mentioned, I'm a language geek. I would have loved to build those things, but it wasn't practical because any one of those would have only given us maybe 2 to 5x performance increase. It's not enough. So a few years ago, you would have heard people say, well, you want to strive for 10x because otherwise you're wasting time compared to Moore's law. But for those of you who were in the talk by the guy with the parallella in his pocket, he'll point out that Moore's law is essentially dead from this point going forward. So I like what they're doing, so I thought I'd change it to, instead of Moore's law, let's just call it Parallella's law. I don't know. I'm sure the industry will come up with some kind of phrase for what's next. So, and for those that aren't familiar with Parallella and the company, they're working on a 1,000-core system, but he couldn't get into too many details. But he said they're working on that now, so it is becoming a reality. And he said this calendar year. So, yeah, so there are all these other approaches that people can take to punt on the other low-hanging fruit. So the classic ones, load balancers and so on. And as far as load balancers, I always take the approach of begin without having a load balancer. You can always add it. That gives you that extra headroom. But it's easy enough to do the routing through software. And I'm talking to an Erlang crowd. You guys get it. So all right, enough said there. So the revised architecture. The top section is the same as before. One process. So everything in one process space on a server instance. One Erlang process per customer. we initially used Amnesia. And when I mentioned that John, a year ago, went to a coffee shop and started working on the pure Erlang version, that version used Amnesia. We knew we would have to replace it because we know that Amnesia will only scale to a certain point. Now, also by mentioning that we have everything in one process space, we are not using the distributed aspects of Erlang. We're using Erlang for the parallel, on the same server concurrency. So anyway, the initial process began with Amnesia, but we eventually moved to ETS. So those who aren't familiar, Amnesia itself is implemented with ETS and DETs, ETS and DETs. So the current version that we have does have ETS, and that's the one that has a bit more than 10x performance increase. But when I submitted the talk, we weren't quite there yet. We hadn't measured it in a production environment yet. So I wasn't comfortable citing those numbers. So some other things to point out. So we have these three forms of data that we store, as I mentioned before. Key value pairs, sets, which are essentially arrays, the way we store it, and the hyperlog, the probabilistic counters. So we have those three structures, and we store it for each day of retention. So say if we store 7 days of retention, we may have an 8th day because we do a modulo table naming scheme, so it wraps around. But we also have to multiply this by the number of customers. So again, if we have 30,000 customers on a box, that's a lot of tables. So, so we haven't stress tested. So I should point out, we have not done full load and capacity testing with that many of customers, but we have done the load and capacity testing with a very high traffic customer, several customers actually. And again, no customer data was harmed in those exercises, usual disclaimers. So previously, we were not using Gen server, or we weren't using many OTP things, but now we are. So one thing to point out, the last line of this slide. We now can accept all data. There's no throttling, no subsampling. We have the capability to do that on a node that sits in front of the Lethe database. And we can do it there if we need to have some kind of brownout situation, overcapacity, denial of service. An interesting thing about denial of service. So it's in the abstract of the talk that our traffic coming into our network appears as a distributed denial of service attack. And when BugSense originally tried to use Amazon, they were shut down in the beginning because Amazon thought they were under attack. Because all these hundreds of millions of mobile devices sending very small messages looks like a distributed denial of service attack. So anyway, but we've worked that out. We're at Amazon now, and we accept all data, no throttling, so consider that a huge success. So now I want to touch on some of the things about the learning curve, my learning curve, and what worked, what didn't work. So what went right, what went wrong, what could be better. So functional programming, I think, is a huge part to explain how we were able to get so much traction so quickly. So the emphasis being on no side effects. So being new to the language, I would write a lot of test code, and I'm sure all of you have been there too, whether it's the hello world type of program or anything beyond that. Well, write it as a test case and leave it as a test case. I mean, there are some really trivial test cases that we have just because I needed to go back and refer to it for my own sanity at times. So I can't stress it enough. And with Erlang, you have eUnit. eUnit is a wonderful tool for those who aren't using it. I highly recommend looking into it. But it also includes a code coverage tool. So we reached 85% code coverage. Well, so actually, it was me. The code base was dumped entirely on my lap. So in 4 months, we were at 85% code coverage. To get to 90% took a bit more effort, and we peaked at about 93%, added a few more features, and it kind of came down again. So test early, test often. Enough probably said about that. But I also want to point out something that went wrong. When we had the Amnesia system, the Amnesia-based system, it would die after 12 hours. So there's a mailbox that's associated with amnesia that under this very high traffic scenario when we were doing our load and capacity testing, I mean, this machine was just being hammered. It would explode after about 12 hours. The Linux out of memory killer would step in and do its thing. So we knew that was going to happen. We put it into that environment because we wanted to see how quickly it would happen. So the amnesia to ETS migration, we hit one, I don't know if it's really an architectural issue, but there were some features of amnesia that we had to reintroduce. And it kind of felt like, well, you know, should I have instead started by forking amnesia? No, don't do it. There's a lot of complexity in there. It was easier to just write the few functions that we needed, like wait for tables and things like that. We did have to introduce one mailbox for the HLLs, for the probabilistic counters, because it's a read, modify, write workflow. So we needed to introduce a synchronization mechanism. Otherwise, with ETS, the Erlang process will block if it can't write because another process is writing. And that model works just fine for our needs. So some of the things that could be better, we're not yet doing Erlang releases for this project, but as of probably a month or so ago, the other guys are starting to go down that path. So we'll probably incorporate that sometime over the summer for here. So pains and pitfalls and so on. You could occasionally hear from my desk, why, Joe, why? So I had a copy of Joe Armstrong's book on my desk, and he kind of became, you know, the scapegoat, if you will, metaphorically. So, but at the end of the day, there's a learning curve, and humans tend to blame their tools, so, you know, no exception here. So again, it goes back to the cartoon at the beginning. Remember to punch holes in the lid. So, you know, a lot of these things seem to be pain points at first, but maybe it was on the earlier slide where I mentioned it. One of the things that I would encourage people to do, especially if you're learning Erlang, rather than use Google to search to find the documentation that you're looking for, you know, like the IO format, you know, to look for the particulars or whatever, learn to navigate the document tree. It will save you grief in the long run, because along the way, you're going to trip over things that you didn't know were there. And anyway, I've done that. I've made that a practice for when I was learning Python in '99, Common Lisp again in 2005, and so on. So I highly recommend taking that approach. But you know, there are elements of the language that are not obvious, that are not intuitive. So for instance, just this week on the Erlang questions mailing list, there was a question about hidden behavior pertaining to the exit message and gen server. So, you know, and it turns out gen server has the terminate function that gets called automatically when the exit message comes. So, you know, learning curve. OK, enough said. So just to start to wrap things up. So beyond that 10x performance increase, if you want to get to the next level, you want the 100x, the 1000x, and so on, the classic approach is focus on reducing contention. So reduce contention for resources. So keep in mind that many Unix system calls, and their equivalent on Windows if you're on that platform and so on, many of the Unix system calls will cause the Beam, will cause your Unix process, will cause the Beam virtual machine to be blocked by the operating system. And a lot of people, I mean, if I were to ask you about that, of course you know that. But when you're writing your code, you don't always think about it. And sometimes you're calling something in an Erlang module, and you don't realize underneath it's actually making a Unix system call. So there's those sorts of things. So what I wanted to call out with this slide are just some of the basic things to look for. Now, keep in mind that when you're doing this, you're essentially doing things that Erlang does for you, that the Beam virtual machine does for you. So then it's sort of turning this talk upside down, because you're going to be writing a LinkedIn module, probably writing in C or C++, and in order to deal with some of these things. So anyway, just to quickly go through these things, to avoid memory allocation or memory construction, in the Lisp world, it's referred to as non-consing, cons being short for construction. I don't know if that term is used elsewhere, but some of the literature will refer to that because, again, Lisp is over 50 years old, so there's a lot of analysis on these techniques in the Lisp world. And I know a lot of people only touched Lisp maybe in college and thought, oh, it's this slow language. But no, actually, it can be very high performance. I know, Erlang conference, enough about Lisp. So, so one of the things about this second bullet point, when you're striving to avoid memory allocation, when you're starting from a language like Erlang, any of these virtual machine-based dynamic languages, you're initially allocating memory in a sandbox. So don't be afraid to populate a list, to generate a tuple, and so on, because that structure is probably only going to be short-lived. The garbage collector will never see it. It will never get promoted to, the larger memory store. So a lot of these are double-edged swords. So be very careful when you're going down these paths. So I called them out so you know what to look for, you know what to think about. But again, tread carefully if you're going down these paths. So one of the things, a whole class of problems that you'll hear from the C10K, C10M. So C10K was concurrent 10,000 connections, and C10M, concurrent 10 million connections. The way to get there on commodity hardware is to move your I/O stack into user land. Again, going back to this first bullet point, you want to avoid Unix system calls that would cause the operating system to block your process. Well, if you don't have to go into the kernel with the system call, you're not blocked. So one of the ways is to move the TCP/IP stack into user land. So the one that is probably the most promising on this list is FreeBSD. They have the libu inet. So it's not UI, it's uinet, userland inet. So they gave a talk in 2014, and at that time, they had about 70% of the performance that FreeBSD's native stack had. But it's important to note, it's the same code that FreeBSD runs. The difference is some data structures that live in the kernel have been moved to user land. So they still have some work to do. And some of the links, one goes to their GitHub page, the other one goes to their presentation. But if that's not an option, you're on Linux, you can't do FreeBSD. At a prior Erlang factory talk, actually 2 prior Erlang factory talks, there were 2 different implementations of moving a TCP/IP stack into Erlang. And should that fail you, going way back to the 1990s, Carnegie Mellon University in standard ML, and there's standard ML, you can, if you squint the right way, it kind of looks like Erlang, maybe. So you may be able to port from standard ML, but you would also need to update because of, changes and optimizations and lessons learned about TCP/IP stacks. So with that, here's a list of references. Again, you'll be able to download all this. So I will open it up to questions if anyone has. Thank you.
Questions in the audience? Anybody? Yes, sir. I should have known if I'd have seen you standing there.
So you said that compare and swap instructions caused a major slowdown. Have you considered some sort of thread local structures that you would update without ever locking the bus?
So yes, we thought about that. And like I said, half of me is sort of the language geek, and the other half would love to go down that path. It just wasn't our core business to do those sorts of things. It was, so if we still ran into problems with the pure Erlang version as an experiment, so back before the ETS version, we would have pursued that if we needed the performance. But it becomes trade-offs at that point. So for an early stage startup that has to keep their operations costs lean, yes, if we ran into problems with Erlang, we would have pursued that, assuming I would have been recruited by the startup. But once Splunk acquired them, so Splunk had its IPO a few years ago, they had their year-end reporting recently, good numbers. So it isn't cost effective in that sense because it'd be easier to just scale back and say, okay, fewer customers per machine, just throw more machines, throw money at the problem. So companies, once they reach a certain point, that's the appropriate business decision for them. But again, as the language geek and so on, yes, I would love to do those sorts of things. But it just, one, we didn't need to. Erlang and ETS performed well enough for us that we didn't need to, so we stopped there.
Other questions? I would like, yes, all right.
So you had on your slide, though you never actually mentioned it, why not LFE? So why not LFE?
Oh, so yeah, at Erlang Factory, San Francisco, last year, Duncan gave a talk. Robert was in the audience. The three of us were chatting after his talk. So the one operator that I pointed out, yeah, the module : function, it came about from that conversation. I mean, Robert was considering it. He had feedback before. So I saw it as a wart at the time because just the : operator, so for those who didn't know, you would have an open parentheses, a colon, space, the module name, space, the function name. It seemed kind of weird to me at the time. So they did fix that. I forget when the code was committed and merged. It was probably about a month later, if memory serves. So the main reason, so again, being a Lisp guy, I would have loved to. The reality was we have other Erlang code bases, and it made sense to keep everything in native Erlang. That said, one of our guys is now playing with Elixir, so go figure. So yeah, that's the answer at the time. I do recommend Lisp-flavored Erlang. So those who are considering it, I do recommend it. It seems to be robust. I don't know what the version is now. I mean, I watch the mailing list, but I don't use it day to day. But you know, I mean, same with Elixir. You know, you're using the same common backend, so there's no reason not to use it. As far as, you know, like JRuby, there in the early days there were pain points there, or JPython before it was Jython, you know, pain points there. You don't have to worry about those issues. So yeah, Lisp-flavored Erlang I would recommend for those who are interested.
Other questions? All right. Thank you very much, Dan.
Thanks.